All right, so hello everybody. Happy Thursday. I am actually in math professional development today, and I want to just go over section 6.5 with you, which is basically how to find any logarithms. And so I want to kind of give you a little background information before we jump into it here. So let's get everything set. All right, so we've done logarithms before, and we did that on your quiz. So you should be able to figure out that the logarithm in base 2, I don't know, something like 8 equals 3 because 10 to the 4th equals 10,000. Or you can take this one right here and you can plug it into your calculator and get the value. What we want to look at today is, what if we have something that's a common logarithm, or excuse me, what if we have something that's a logarithm like this, logarithm base 3 of 12, okay? We know that that answer is going to be somewhere between 2 point something, okay, because it's going to be between 2 and 3. How do we figure out what that is as a decimal? Well, we could sit here and guess and go 3 to the 2.1, get an answer, 3 to the 2.2, get an answer, and kind of keep going and simplify it that way. But there's a different way, a much easier way, and that's called the change of base formula. So let's take a look at that. And we're actually going to go through this whole thing. It's a lot of material, but it's pretty simple and straightforward, I hope. So the change of base formula says this. It says the logarithm of base b of the number a equals the logarithm of a, whatever this number is, divided by the logarithm of b. And you can also do that with natural logarithms. Here, if I have the logarithm in base b of a, that equals the natural log of a over the natural log of b. Okay? And this is a nice way to find any logarithm. And the cool thing about this is that this and that can be done on the calculator. Done on your calculator. So that makes it really convenient for us. So let's take a look at these examples here, and you'll see just how fast it goes. So logarithm, so evaluate the logarithm in base 3 of 8 using common logarithms. So we know logarithm base 3 of 8, we know that's not going to come out as a nice integer exponent. It's going to be 1 point something, I'm thinking. So we can redo this as the logarithm of 8 divided by the logarithm of 3, and we grab our handy dandy calculator and clear that out, and we simply, here's our log button right here, logarithm of 8 divided by the logarithm of 3, and we get about, let's say, 1.893. Now here's the cool thing, way to test this. I know I should be able to take 3 raised to the 1.893, and I should get around 8 for my answer. And you can see I do, it's a little off because of rounding. So that means that the logarithm in base 3 of 8 is equal to that, but it's also equal to 1.893, remembering that logarithms are just finding exponents is what we're looking at. All right, we can do this one down here also. Logarithm base 7 of 11. It's the log of 11 divided by the log of 7. And so when we put that into our calculator, let's see here, logarithm of 11 divided by the logarithm of 7. And we should once again get 1.232. Okay. 232. We can also use the natural log, so I just want to show you that real quick. If I have the logarithm in base 6 of 24, we can say the natural log of 24 over the natural log of 6. And what's that look like? So our natural log button is right here, natural log of 24 divided by the natural log of 6. And we get 1.773, 1.774. If that's correct, we should be able to take 6. Let's see. Clear that out. Clear that out. So we should be able to take 6 raised to the 1.774 And notice we get about 24. So we're good. So 1.774. Okay, so that's the change of base formula. It allows you to find any logarithm, even when it comes out not as an integer. All right, cool. Next thing on our list, though, let's talk about properties of logarithms. So basically, these are things that are not quite as relevant anymore because with the advent of technology, but they're still good mathematical processes to know, and so we're going to go over them. So think about your exponent rules. Think about if you have two things and you multiply them together, what do you do with the exponents? You add them. Product. What if you have two things, two variables that you are dividing, and what do you do with their exponents? You subtract them. So properties of logarithms kind of follow the properties of our exponents. So what that means is that I take the logarithm of two things multiplied together, m times n. That is going to be equal to the logarithm of the first one, which is m, plus the logarithm of the second one, which is n. Okay? Rules of exponents. Your second property, quotient property, what if we have a fraction of m over n? What does that equal? Well, it's the logarithm of your numerator, so the logarithm of m minus the logarithm of your denominator. Right? And the third one, we use this one a lot. Okay, what if I have the logarithm of m raised to the x power? So I've got an exponent here. And like I said, this is the one that will be used the most often. This is the one that I personally feel is most important. What we can do is we can take this exponent that's right here and we can bring it out front and make it a multiplier. So the logarithm of m raised to the x power is equal to x times the log of m. And so some just kind of basic problems that we can look at. If we look here at example 3, the logarithm base 2 of 3 is approximately 1.585, and the logarithm base 2 of 7 is approximately 2.807. We want you to evaluate the following things. So if I have this logarithm base 2 of 3/7, what I can do if I want to rewrite that using my properties, since I have a division, it is going to be the quotient rule, which means I have to take the logarithm base 2 of 3, and I'm going to subtract the logarithm in base 2 of 7. Knowing that the logarithm base 2 of 3 has a value of 1.585, and the logarithm base 2 of 7 has a value of 2.807, we can substitute those numbers in. And then if we do a simple subtraction, 1.585 minus 2.807, we get an answer of negative 1.22. Similarly, we can take a problem like this, logarithm base 2 of 21, and we can use these things up here because we know that 21 is really 3 times 7. And so we can use the product property, and we can rewrite this as the logarithm in base 2 of 3 plus the logarithm in base 2 of 7. Once again, knowing what these two things are equal to, 1.585 plus 2.807, we can come up with an answer of 4.392. Okay, so the logarithm base 2 of 21 is 4.392, and if you think about it, 2 to the 4th is 16, 2 to the 5th is 32, so it should make sense that the logarithm base 2 of 21 is around somewhere between 4 and 5. All right, and lastly, logarithm base 2 of 49. We can use this property right here because we know that 49 is 7 squared. And so we can say the logarithm base 2 of 7 squared. We can take this 2 and bring it out front. 2 times the logarithm in base 2 of 7. And logarithm base 2 of 7 is 2.807, so it becomes 2 times 2.807. And when you multiply those two things out, you get 5.614. So that means 2 raised to the 5.614 is approximately 49. All right, so that's using those things with numbers. On the next side, we're going to look at, I just find this to be fun. So this is just some old school hardcore mathematics that is just a good time. So we have the natural log of 5x to the 7th divided by y, and we want to expand the logarithmic expression. Anytime we are expanding the logarithmic expression, we have to get rid of anything that's multiplied or divide. We have to separate those, is what I should say. And we have to take care of all of our exponents. So the first thing I want to do, because I have a division here, division means subtract. So I want to take the natural log of the numerator, 5x to the 7th, and I want to subtract off the natural log of the denominator. So that's my first step. Okay? This one is all taken care of, this part, but I got to work here some more. So the next thing I got to do, since this is 5 times x to the 7th, I got to separate the 5 and the x to the 7th. And since it's a multiplication, I'll separate it by an addition. So I'm going to take the natural log of 5 plus the natural log of x to the 7th, and then keep my natural log of y, ln of y. Okay? Hopefully you see how I took this multiplication and separated each piece into its own natural log with an addition between them. The last thing we want to do is take care of this exponent. So I'm going to take this 7 and bring it out front. So I'm going to have natural log of 5 plus 7 times the natural log of x, minus the natural log of y. And here's our final answer. Notice each thing is separated. So we started with 5, x to the 7th, and y. They're all separated into their own log. Since it was multiply here, I put a plus, and since it's a division here, I put a minus. And notice that my exponents are moved out front. Okay? All right, for example 5, we're going to do the reverse. We're given something like this, and we want to take care of this and rewrite this so it looks like that. So we got to do the reverse process. So the first thing we want to do is any numbers that are out in front of our logs, we want to make them exponents. So I'm going to write this as the log of 9 plus the logarithm of 2 to the 3rd power minus the logarithm of 3. Okay? All right, so we've got that. So now what we want to do is we want to combine things. And we can kind of think of this logically and do it in one step. We know if we have an addition here, when we combine it, we're going to take that number times that number. So I'm going to go with the logarithm of 9 times 2 to the 3rd. And this subtraction means divide. And so that's what we end up with, 9 times 2 to the 3rd divided by 3. Now we got to go ahead and compute what 9 times 2 to the 3rd divided by 3 is. So 9 times 8 is 72. Divide 72 by 3. Here, let me write this out. So we got the logarithm of 72 over 3, which equals the logarithm. Let's see, that goes in there twice. We get the remainder of 1, so it goes into 12, I believe. Log of 24 is the answer. Okay? And since it's condensing, we can leave it like that. If we wanted to compute the log of 24 in our calculator, that would be fine. But we don't have to. All right, finally, let's take a look at this problem right here. Okay? For sound intensity I in watts per square meter, the loudness of the sound in decibels, some of you music heads who have big stereos might know a little bit about this, anyway, is given by this function. L of I equals 10 times the log of 1 of I, which is the intensity, over the initial intensity. So I sub 0 is the intensity of a barely audible sound. An artist in a recording studio turns up the volume so that of the track so the intensity of the sound doubles. By how many decibels does the sound increase? So basically we want to look at since L is the loudness, so we want to figure out how much does the loudness increase. How much does the loudness increase when we double the intensity as compared to the loudness of the original intensity? So here I put a 2 out here because that's my double intensity and that's my original. And it says how many does it decrease, so we want to find the difference. How much does it go up? So what's that look like? So I got to take this here and plug 2i into there. And so I get 10 times the log of, I'm going to plug 2i in for I. So it's going to be 2i over I sub 0 minus this one right here, which is just going to be 10 times the log of I over I sub 0. All right, so we need to simplify all this a little bit. So the first thing I'm going to do, since both of these have 10s in them, let's factor that 10 out so that we're just working just with the logs. So if I factor a 10 out, I've got the log of 2i over I sub 0 minus the log of I over I sub 0. Okay? Cool? All right, notice I have a subtraction here. So if I want to combine those two things, what I can do is I can divide those two things, right? I can divide this and this by this. So I'm going to write it a little differently. So I have 10 times the log of 2i over I sub 0 divided by I over I sub 0. Okay? Now, this is a division, dividing by a fraction. So when we divide by a fraction, what do? Keep it, change it, flip it. So I got 10 times the log of 2i over, made it a little big this time, 2i over I sub 0 times I sub 0 over I. Now, some things can cancel. First of all, the I sub 0s can cancel right there. And this I can cancel there. And so what I'm left with after all of that canceling is 10 times the log of 2. Which looks like that. And
Sophia Tesmer comes to the office. Sophia Tesmer to the office.
That you can type into your calculator. 10 times the log of 2. 10 log of 2, and it comes out to about 3 times as loud. So approximately 3 times as loud. All right, that one's a little crazy because you had to know how many decibels is the loudest increase. So from here to here, how much does it go up? Well, you got to subtract that off of there. So this equation, I plugged in 2i for I. This equation, I plugged I in for I. Took out my 10, okay, as a greatest common factor. And then from this step, I said, hey, I got a division, subtraction, so I can change it to a division when I combine them. How do you divide fractions? Keep it, change it, flip it. And then once I kept it, changed it, flipped it, you can cancel things out. Ended up with a numerical thing of 10 log of 2. Plug that into the calculator, and you get 3 times as loud, approximately. All right, that is